Hello students, today we will discuss about relation and ordering. So first of all we should know what is relation. So relation, that is in our daily life, in our everyday life, businesses and their telephone numbers, employees and their salaries, students, their colleges, etc. are in our daily life relationships. So relationship can be used to solve problems such as determining which pair of cities link with airlines, which pair of cities link with train lines and buses, etc. In many problems, find a suitable order for the different phases of a complicated project. So relationship is very important. So in mathematically, let A and B be two sets. A binary relation R is a subset of A cross B. From this definition 1, the binary relation R is a subset of AB such that A belongs to A and B belongs to B. When AB belongs to B, A is said to belongs to R. And sometimes we use ARB to denote AB belongs to R and A not related to B to AB not related to R. Here, let this example 1, A be the set of students and let B be the set of courses. Define R to be the relation that consists of those pair of students, those pair of AB where A is student enrolled in course B. So this is R is equal to AB such that A belongs to A and B belongs to B. Students A enrolled in course B. Example 2, this is let A be the set of all cities and B be the set of 50 states in India. Define the relation R by specifying that AB belongs to R if city A is in state B. For example, Ahmedabad, Gujarat, Mumbai, Maharashtra, Panaji, Goa, Bhubaneswar, Odisha, Udaipur, Rajasthan and etc. So let this example 3, let A equal to 0, 1, 2 and B be AB. So let R be a relation, that is 0A, 0B, 1A, 2B is a relation from A to B. This is the graph. 0, 1, 2 related with 0 is related with A and B and 1 related to A, 2 related to B. So relation on set. What is the relation on set? A relation R on a set A is a relation from A to A, that is R is a subset of AB for all A belongs to A and B belongs to A. Example 4, that is let A be the set 1, 2, 3, 4 which order pair are in the relation R equal to AB where A divides B. The solution are 1, 1, 1, 2, 1, 3, 1, 4, 2, 2, 2, 4, 3, 3, 4, 4. These are all pairs where A divides B. So let example 5, that is consider the following relation on the set of integers. These are the relation R1 to R6. R1, R2, R3, R4, R5 and R6 are the relation. Which of this relation contain each of 1, 1, 1, 2, 2, 1, 1 minus 1 and 2, 2. We have to find all that relation which contain this pair of elements. The solution is 1, 1 contained in R1, R3, R4 and R6. Whereas 1, 2 relation is in the set R1, R6 and 2, 1 belongs to R2, R5, R6 where 1 minus 1 pair is belongs to R2, R3, R6 and finally 2, 2 belongs to R3, R1 and R4. So now properties of the relations. So this is the first property, that is a relation R on a set A is called reflexive if A belongs to R for every element A belongs to A. So consider this example where 1, 2, 3, 4 are the set. We have to follow the relation on this set. Let these are the 6 relations. This also R1, R2, R3, R4, R5 and R6. These are the 6 relations. Now our question is, which of these relations are reflexive? Here these are the solution, but R3, R5 are reflexive. How is it possible? See, in this case, our definition says 1, 1 belongs to R. In R3 and R5, R5 1 1 1 2 1 4 2 1 2 2 3 3, all the elements belong to this, and R5 also 1 1 2 2 3 3 4 4 belongs to the reflexive. But in R1 3 4 is present but 4 3 is not present. In R2, R5, R4, R6 similarly a condition is that which not satisfy the condition. For example 7, consider the following relation on the set of integers where these are the same 6 sets, but we have to also find out which is reflexive. Here special cases is there. Here R1, R3, R4 are reflexive. For the case R1, AB belongs such that A is less than equal to B. Wherever we say 1, 2, 3, 5, 7, 9, they all belongs to R1 case, and again the other will also satisfy this. But here AA means that belongs to R1 and R3 and R4. Next is the divides relation on the set of a positive integer reflexive. So this is the solution. It is reflexive since AA, whenever A is positive integer. Okay, so in the last one, okay, it is reflexive AA whenever A is a positive integer, means 2 divides 2, 3 divides 3. In the positive integer set, every element which is positive integer that always divide itself. So it is a reflexive condition, or it satisfies the reflexive condition, or it satisfies the reflexive relationship. Okay, for the next, this is the second condition. A relation R on a set A is called symmetric if BA belongs to R whenever AB belongs to R, for any AB belongs to A. Again, a relation R on a set A such that AB belongs to R and BA belongs to R if and only if A equal to B. For any AB belongs to A is called antisymmetric. Now consider this example. The set is 1, 2, 3, 4. Here these are the 6 relations. Which of this relation is symmetric? Which is antisymmetric? So for R2 and R3, case 1, 1 1 belongs to R2, 1 2 which opposite is 2 1 that belongs to also R2. That's where R2 is symmetric. For the case of R3, 1 2 2 1 1 1 2 1 4 4 1, every element and its opposite also belongs to the same set, that same R3. That's why R1, R2 and R3 are symmetric. But in cases of R4, R5, R6, in the case of R4, we have this element 4 1 whose opposite 1 4 is not present, and also that is not equal. So R4 is not symmetric, that is antisymmetric. In R5 also 1 3 3 1 is not present. In R6 there is single element, so we can't say anything. That is the next example here. Here also consider the following relations on the set of integers. That are the relation AB, that is R1, such that A is less than equal to B. R2 is A belongs to A. R3 means A equal to B or A equal to minus B. R4 equal to A equal to B. R5 equal to A equal to B plus 1. R6 equal to A plus B, that is less than equal to 3. So in these cases, for the R3, R4 and R6 are symmetric, because in R3 whatever we may take A equal to 3 or minus 3, we can take is a symmetric position. For R4, A equal to B, whatever we take, 1 is equal to 1, 2 equal to 2, so this must be symmetric. R6, A plus B less than equal to 3, 1 plus 2 less than equal to 3, 0 plus 2 less than equal to 3. Similarly, for R1, R2, R4 and R5, these are anti-symmetric. We can take opposite of this. Example next. Is the divide relation on the set of positive integers symmetric? It is antisymmetric. It is not symmetric since 1 2, 1 divides 2, but 2 doesn't divide 1. It is antisymmetric since for any positive integer A and B with A divides B and B divides A, then A equal to B. It's a special case If A equal to B, then only the condition are vice versa. So this is the transitive. This is the third important relationship. A relation R on a set is called transitive if whenever AB belongs to R and BC belongs to R, then AC must belong to R for any ABC belongs to A. This the condition. This is the example. Let's the same example 1, 2, 3, 4 belongs to a set. The set contains only 4 elements. These are 1, 2, 3, 4. So here R1, R2, R3, 2, R6 are the relation. And which relation is transitive? Here R4 and R6 are transitive. Let's see. In R1, 1, 1 is present, 1, 2 is present, 2, 4 is present, 2, 3 is present, 2, 3 is not present, 2, 3, 4 is present, but 4, 3 is not present. Okay, 3, 4 is present and 4, 1 is present. But 3 and 1 that is not present, so it is not transitive. For our two cases 1, 2, 2, 1, 1, 1 present and 2, 1, 1, 1, 1, 2 cases present, but 2, 2 is not present. In R4 1, 2 present, 1, 2, 2, 1 present, 3, 1 present, 4, 1 present, every combination 4, 1 and 1, 4 is not present, so 4, 2, 2, 1, 4, 2, 2, 1, last elements are 4 and 1 that is present. R4 is transitive, 3, 4 that is single element that is transitive, and the rest are not transitive. Now this is the example where same 6 conditions is there, 6 relations is there. Here also R1, R2, R3 and R4 are transitive and others are not. Again divides condition for positive integer. Every A divides B and B divides C. For all A, B and B, C, A divides C. For example 2, 3 and 3, 6. 2 divides 6. This is the equivalent relation condition. Relation on A is called an equivalent relation if it is reflexive, symmetric and transitive. Means relation on A is called equivalent relation if satisfy the 3 conditions what we taught recently: reflexive condition, symmetric condition and transitive condition. Then you can say the relation is equivalent relation. Means 2 elements are related by an equivalent relation are called equivalent. Okay, that this example is taken. A be a set of string of English letter and LX be the length of the string X. So letter relation R equal to AB where AB belongs to A and length of A equal to length of B. Is R is the equivalent relation? Yes. Here R is reflexive, symmetric, transitive, so it is a reflexive relation. For AB, length of A is always fixed. For 2 element AB, if length of AB, length of A to B must equal to length of B to A. Again, if we are taking length of AB and BC, there are 2 lengths, so ACB there must be a length that is equal to AC length is CA length. So this is a equivalent relationship. Next, this is the second example. Let R be a relation on a set